Good evening, and thank you for joining us on Zoom webinar. I'm Eric Walker, Chair of Highlands Astronomical Society, and it's my pleasure to welcome club members of old and all our new members who have joined over the past month. Also, visitors from our North of Scotland sister astronomy clubs, and to the first-time visitors who have contacted us wanting to find out what we get up to at our monthly club meetings. Tonight, after this chairman's chat, we'll go straight into our main talk, followed by questions and answers. About 8:30, we'll do our club news, astro picks and targets for the month. Just before 9 o'clock, probably, we'll do a wrap up, and that will take us to the meeting close. Now, last month, we had a post-meeting Zoom blether, and we're going to do that again. There will be a link which will be provided in a chat box near the end, and we'll explain in more detail how you actually use that and can come along for a chat after. As usual, there won't be any breaks during the meeting, so if you need to leave for any reason, just get up and go, but keep yourself connected to the meeting. If you have any questions for the speaker or the club, please put them into the Q&A section at any time during the meeting, and we'll pick them up and ask the speaker. Any problems, click the hand icon and someone will get in touch with you directly via chat, and use the chat for general chit chat. So, what have we been getting up to? Well, the weather has been much kinder to us over the past few weeks, and we've seen a lot of observing activity from our own and affiliated club members. There's been beautiful photographs of the Northern Lights, the moon, superb deep sky astrophotographs, which Pauline will be showing you many of these later in the evening. We've held a couple of very successful and well-attended live observing webcasts, one dark sky session and one lunar observing session. Great fun, lots of viewer interaction on the YouTube live chat, and we can't wait to run a few more throughout March. The sun's also becoming more active, and you'll be pleased to know we can run live solar observing webcasts during the day, so watch this space. In fact, the best way to watch this space is for members to join our WhatsApp groups and receive notice, often very short notice, of the forthcoming live observing webcast. WhatsApp is proving increasingly popular amongst members, judging by the interaction and comments we are seeing, and it's now our default method of letting people know what's about to happen. Please contact Lorraine Shepherd, our membership secretary, to get set up with our WhatsApp groups. The all-sky camera continues to be an outstanding success, and last month captured an image of a rare fireball or bolide. And it also clarified a local report from a very excited observer of a potential UFO sighting. It turned out to be high-altitude military aircraft practicing a late-night rendezvous or refueling exercise, but it was great fun to investigate nonetheless. Now, under the Scottish Charities Regulator rules, I have to formally notify members that our annual general meeting will be held in April at our next scheduled club meeting on Tuesday, the 6th of April, 2021. Because of the ongoing situation, it's been decided that the office bearers will remain in position. The chairman, Eric Walker, secretary, Rona Fraser, and treasurer, Andy Brough. However, if you wish to stand or nominate anyone, please let our club secretary, Rona Fraser, know in good time. We'll be preparing next year's annual operating plan and budget on the basis of how we have operated the club in previous years. Nevertheless, we anticipate well, we know that things have changed significantly. And in the next couple of months, your committee will be revising how your club is going to operate in the future. For example, monthly meeting attendances have been at least as good and sometimes doubled since we have presented them online. There's a large interest, attendance and interaction in our live observing webcast sessions. We get 20 to 30 attendees per session, much more than we're used to up at the JSL Observatory. The informal formation of the North of Scotland Amateur Astronomy Association, NOSA, has been an astounding success in achieving collaboration across like-minded astronomy clubs and groups, and is something that needs to be built upon. Surprisingly, and most beneficial to our club, is that we have increased our membership to 64 from 42 last April, with several new membership queries still in the pipeline. This is a great achievement and indicates the level of amateur astronomy interest in our and wider areas, and the potential for growing our club. Key areas of concern are the lack of social interaction and practical, on-the-ground observing astronomy and astrophotography. This has been particularly highlighted due to the current COVID restrictions, but to be honest, it wasn't that great beforehand, and we need to look at ways of improving this and get back the club feel. To this end, I'm asking members for ideas, suggestions, creative constructs for us, your committee, to consider when reformulating the way your club is run. Please contact Club Secretary Rona Fraser as soon as you can with your suggestions. We often get no response to requests like this, but this is so important now, and we want you to help reshape your club. In addition, if there are any items for the agenda, again, please let Rona know. And so, back to tonight's meeting. I'm going to introduce our main speaker for tonight, Martin Henry. Martin Henry is no stranger to us here at Highlands Astronomical Society, nor to attendees of Orkney International Science Festival, where he has delivered several groundbreaking talks in recent years. Martin is Professor of Gravitational Astrophysics and Cosmology at the University of Glasgow, where he has also recently ended an 8-year term as the head of the School of Physics and Astronomy. He's a senior member of the LIGO Scientific Collaboration, the global team of more than 1,300 scientists who were responsible for the first ever direct detection of gravitational waves, a discovery that was awarded the Nobel Prize for Physics in 2017. Martin currently chairs the LSC Communications and Education Division and is responsible for coordinating LIGO's ongoing discovery announcements, including, for example, their new catalogue of 50 confirmed gravitational wave detections announced in autumn 2020. Martin is also a fellow of the Institute of Physics and the Royal Society of Edinburgh. It's with great pleasure that I welcome Martin to be with us tonight. And here he is to talk about the darker things in life. No, not COVID. Martin Henry, exploring the dark side of the universe. Over to you, Martin.
Thank you very much, Eric, for those very kind words, and a very warm welcome and hello to everyone who's watching along online. It's a real pleasure to be with you, even if, of course, we would all rather be able to meet face to face. And it was very interesting just to reflect on some of Eric's comments about the way in which your meeting membership and your meeting attendance has been boosted during lockdown. So here I am broadcasting from my kitchen, so to speak, and it's been a real pleasure to be able to do this throughout the last year. It's been a journey for me, because although I've been accustomed to a lot of my research, especially with LIGO, involving remote participation and endless telecons. Something I've always enjoyed throughout my career is being able to come and actually visit astronomy societies and clubs around the country. So to be able to join you at least online does feel strange, especially given the many visits I've made that I look back on so fondly to the Highland Astronomy Society in the past. But I'm at least pleased that I'm able to join you in this way. And let me just get the full screen going. And oops, that wasn't quite supposed to happen. So you'll get the first bit at the top in reverse, so to speak. It's as if you're watching Tenet tonight, but there you go. You should now be looking at the opening slide, exploring the dark side of the universe, as Neil, as Eric introduced. So what I'm going to talk about tonight is a little bit about gravitational waves right at the end, but in fact, mainly what I'm going to cover is the broader sweep of what we call cosmology, the study of the universe on its largest scales. And I'm going to be looking at what we've learned in the last few decades that has led us to a rather odd and slightly uncomfortable place where our picture of the universe is starting to show maybe just a few concerns about exactly how everything fits together. I'm reminded, for example, that the very first time I came to visit the Highland Astronomy Society, the first talk I gave was in the spring of 1998. And it's a scary thought to think that that's 23 years ago. And the reason I remember is that it was around the time I was beginning to teach our first year cosmology course. So I was writing some of the lectures on the way up on the bus, would you believe? And over the weeks that followed after my talk, gradually pulled everything together. But I do remember trying to think, what am I going to cover in these first year lectures? And the reason that wasn't at all obvious is that I had been a student in Glasgow myself, but the field of cosmology had changed a lot, even just in the, 15 years or so since I was learning it as a student myself, to then go to be teaching our first years. And chiefly, what we had learned in that time is that our universe seems to be dominated by what we now call dark matter and dark energy. The second part, the dark energy part, really was hot off the press back then. In 1998 was just when we were beginning to realize that something was causing the expansion of the universe to speed up. So I think I had the chance, even back then, maybe some of you can remember, to talk about some of that, like I said, hot off the press back in the spring of 98. But a lot's happened since then. And I've probably touched on those themes when I've come up to do other lectures in the years in between. But I thought it might be useful, especially for those who weren't any of those previous lectures, to just take this chance to review what we've learned about the dark side of the universe and where it seems to be leading us now. The other thing I should say, and perhaps I've also talked about this on previous trips up to give lectures in Inverness, is that I'm a huge Star Wars fan. So you might think, giving my talk the title Exploring the Dark Side of the Universe, that you're going to get a talk about this chap here. And well, there's some degree of truth in that, because even if it's not going to be about Darth Vader, it's certainly going to be a talk about this, because those famous words that you see at the start of all the Star Wars films, those really were a source of inspiration to me as a youngster watching Star Wars. I think it was about 10 when I saw episode 4 for the first time. And little did I know then that I would wind up as a cosmologist, more or less day on day, studying what was happening a long time ago in galaxies that are far, far away. And that's really the key to how we have learned so much about the universe, even if it's led us to this rather odd place where it seems as if most of the matter and energy in the universe is in this mysterious dark form that we can't actually see. And one of the instruments that's really helped us get there is the Hubble Space Telescope. So it was launched in 1990, just shortly after I'd finished my degree, and I was doing my PhD at that time. And some of my PhD work was using data from the Hubble Space Telescope to try and measure the size of the universe. And all these years later, Hubble is continuing to have interesting things to say about questions around that, around how big the universe is, how fast it's expanding, and what it might do in the future. But if we go back to the early 20th century, before we talk about the Hubble Space Telescope, we need to talk about Hubble himself. The Space Telescope is named after Edwin Hubble, who many people would regard as almost the godfather of cosmology, because before Hubble came on the scene in the early decades of the 20th century, our perception of the universe was very different indeed. We had, by that point, mapped out reasonably well quite a lot of the Milky Way galaxy. Not as well as today, but we had this sense of the solar system being part of this island of stars, a vast number of stars that we call the Milky Way. But what we also observed were lots of objects that we called at the time nebulae, meaning gas clouds. And there was a very important and unanswered question that were in the minds of astronomers at that time. The question was, are these nebulae gas clouds within the Milky Way, or are they completely separate galaxies altogether, what were rather poetically referred to as island universes? And key to answering this question was Edwin Hubble, but he by no means did it alone. In fact, he principally was drawing upon the excellent contributions of Henrietta Swan Leavitt, who was working at the Harvard Observatory in the decades just before Hubble began to unlock the mysteries of cosmology. And what Leavitt was doing was studying a particular type of star. These stars are called Cepheids, and they vary in their brightness. Now, no one's ever seen a Cepheid like the cartoon animation that's showing in the bottom left corner. But what we think is causing the Cepheids to change in brightness is that they're actually changing in size. They're pulsating in and out, and it's driven by physics that's going on inside the star as it reaches a certain stage in its lifetime, turning hydrogen into helium and using that as a source of its brightness, of its luminosity. So these are very highly luminous stars, but the change in their brightness gives them another extremely useful characteristic, which Henrietta Swan Leavitt was the first person to deduce. So the way she did this was by looking at Cepheid variable stars in the Magellanic Clouds, the two satellite galaxies, which are companions of the Milky Way. We know that now, and they're observable in the southern hemisphere. So the image you see in the top left is from the Paranal Observatory in Chile, and it's showing the two Magellanic Clouds clearly visible against a rich star background. Now, these Magellanic Clouds are quite far away. We now regard them as about 150,000 light years from the solar system. Now, Henrietta Leavitt didn't know exactly how far away they were, but she deduced that they were far enough away that if she saw Cepheid variables in the Magellanic Clouds that appeared to be different in brightness, it's because they really were different in brightness, not because one was further than the other, because essentially they were both at more or less the same distance. It's like asking, from the perspective of someone up in Inverness, how far away is London King's Cross Station versus how far away is London Euston Station? From the perspective of Northern Scotland, they're essentially the same distance away. So knowing this, and knowing that differences in their apparent brightness could be related directly to differences in their true brightness, what Henrietta Swan Leavitt was able to deduce was that there's a relationship between the brightness or luminosity of these Cepheid stars and the period of their pulsation, how long it takes them to pulsate in and out. And that's what you've been watching for these few minutes. I'm not trying to hypnotize the audience, but that little animation is showing you that the more luminous Cepheid, the one on the right, which gets much larger, also takes a longer time to go through its pulsational cycle. And this was enormously useful. It straight away provided Edwin Hubble with a way to measure distances to those island universes, those nebulae, where there was an open question, were they in the Milky Way or did they lie beyond? So this was equivalent to knowing how powerful a light bulb is, knowing if it's 1000 watts or only 10 watts. A 1000 watt light bulb, if it was taken 10 times further away, would appear as bright, or maybe I should say as dim, as a 10 watt light bulb at the original distance. So obviously stars don't have their wattage written plainly on for astronomers to see, but Henrietta Leavitt's work provided a way to deduce that luminosity, to know effectively whether a Cepheid was 1000 watts or 10 watts. So Edwin Hubble was able to use that information, and he did it using the 100-inch Hooker reflector at Mount Wilson, just outside of Pasadena. Now that's not such a good location for stargazing these days because of all this, the light pollution in the greater Los Angeles area. You can see that in the lower right. But back in the 1920s, this was probably the best telescope in the world. It certainly had the best opportunity to view the distant universe because of the many, many nights of clear skies that the Mount Wilson Observatory enjoyed. So what Hubble was able to do was observe some of these Cepheid variables in some of these nearby nebulae. But he discovered that they weren't quite as nearby as some astronomers had speculated. Those who had argued that they were actually just gas clouds within the Milky Way, well, Hubble's work overturned all that. Even the nearest one, the Great Nebula in Andromeda, was shown to be more than 2 million light years away. In other words, it lay outside of the Milky Way galaxy altogether. And Hubble managed to do this by identifying these Cepheid variables, shown by the little red arrows in his photographic plates, within the Andromeda, what we then called the nebula, but we really should now start to call the Andromeda galaxy, because Hubble established that it was a whole separate galaxy beyond the Milky Way. Now, here's a modern day image of the Andromeda galaxy, and we see that it's a grand design spiral. That's actually rather similar to the Milky Way itself. If anything, it's slightly bigger, but at a distance of about 2.5 million light years, this is one of our nearest neighbors in the universe. And Hubble's observations allowed him to piece together a picture of the local neighborhood. So what we are looking at here is a kind of Star Trek style animation of what Hubble effectively was able to learn about our nearest neighbors. We've just passed Andromeda. We're heading through other nearby galaxies. We're going to end our journey in the cluster of galaxies that we call the Virgo cluster. That's about 60 million light years from the solar system. So even within just that local patch of the universe, there are hundreds of galaxies, and Hubble was able to measure distances to a decent fraction of those. And that's what led him to a quite remarkable discovery. Now, that discovery was made possible not just by measuring the distances, but also by measuring a property that we call the redshift of each galaxy. Now, that redshift is brought about, we believe, by the expansion of the universe. But it's essentially, from a physics point of view, a similar phenomenon to what happens when you have a moving source of light. So a star, or indeed a galaxy, moving through the universe rather than the universe itself expanding. So that means to say, this is essentially like the so-called Doppler effect. When you have a source of sound waves moving, then we hear a change in the pitch, the frequency of the sound. Likewise, with a source of light, you get a change in the frequency and the wavelength of the light. And what Hubble found was that generally galaxies displayed a redshift. The lines in their spectrum were shifted towards redder colors. Here's that Doppler effect. we are changing the pitch of a sound wave, as for example, a car horn is heard passing by. But as I was saying, for light, we get the same effect. We get red shifting for a source of light moving away. We get blue shifting for it moving towards. Now, as I said, Hubble's observations led to quite a remarkable discovery. And that discovery was aligned with theoretical work that had been done by Georges Lemaitre. So just a few years ago, what had previously been referred to as the Hubble law has now been renamed the Hubble-Lemaitre law in recognition of that sort of marriage of observations and theoretical underpinnings. And that Hubble-Lemaitre law basically says that the further away an object is, the more rapidly it will appear to be receding from us. And we interpret that as due to the expansion of the universe, as illustrated in the cartoon here. Now, to some extent, this is all old news. And for many listening this evening, I'm sure you're broadly familiar with everything I've said so far. So let's try and bring things a bit more up to date. Firstly, we notice that over the course of the 20th century, the slope of that relation in the previous slide, well, our ability to measure that changed quite dramatically. So Hubble established that there was this straight line relation. Let's go back and look at it one more time. His data were far from perfect, but the trend is very clear. But the slope of that straight line, which gives a kind of measure of the age of the universe, well, unfortunately, Hubble got that spectacularly wrong. His initial estimate would have made the age of the universe embarrassingly young, compared with even the age of the Earth that was reasonably well estimated by then, due to, for example, paleontology or geology. But that's because of a combination of factors that meant that Hubble had, well, to quote George Bush, misunderestimated certain of his observations. Both the distances and indeed the velocities that he was measuring and interpreting as redshifts were subject to what we call systematic errors. And gradually over the 20th century, those errors were identified and partially at least eliminated. And all of that drove this number that we call the Hubble constant, the expansion rate of the universe. It drove that number down. So you might say Hubble constant seems a rather poor name because in fact it wasn't constant even over the 20th century, but that's more a reflection on our improving abilities to measure it rather than any actual change in the number itself. But by about the 1970s and 1980s, the value had settled round about the range 50 to 100 in the appropriate units. Those units are kilometers per second per megaparsec. A megaparsec is about 3.25 million light years. So this number is basically telling us, as you go further and further into the universe, how much faster are galaxies appearing to recede from us. So when I was beginning my studies in the 80s, we had pinned down this Hubble constant, as I said, to somewhere between 50 and 100 kilometers per second per megaparsec. But rather embarrassingly, there seemed to be a real split in the values that astronomers were obtaining. Some were arguing passionately that it was round about 50, while others were arguing equally passionately that it was round about 100. And then around then, the Hubble Space Telescope enters the scene. And one of its key tasks was to try to improve our estimate of the Hubble constant, to try to resolve this dispute between those who argued it was 50 and those who argued it was 100. So over the course of about 20 years, that estimation improved leaps and bounds, largely because what the Hubble telescope was able to do was to take measurements much, much further than Hubble himself had been able to. So the range covered by Hubble's original measurements is just down here in the very corner of this graph. So that's the original plot from Hubble. You could fit that into the first tick box on this graph here. But thanks to the Hubble telescope and other projects in the 1990s and early 2000s, we were able to take the measurements much deeper into the universe and refine them to make them much more precise. And ironically, the value that seemed to emerge from all of that was almost exactly halfway between what people had argued for before. It wasn't 50, it wasn't 100, it was about 72 or so. So, of course, some people joked that all we'd had to do in the past was just average everyone's results and we would have got the right answer. But it was much more reassuring to have arrived at that place with more reliable measurements, less prone to systematic errors. Now, the improvements continued. So the Hubble Key Project reported its results in 2001, 20 years ago. And that basically got the error, the uncertainty on the Hubble constant, down to about 10%. But in the 20 years since then, the quest has been to try and get it down to about 1%. And we're not quite there yet, but almost. And the most recent kind of results have been coming in with uncertainties about 2% or thereabouts. And a good example, again, this looks rather complicated, don't panic, but this is just to let you see the very latest state of the art. This is a paper that was published on the internet on January 2nd, and it's to do with a satellite mission that you may have heard about called Gaia, that has been mapping our galaxy to incredible detail, mapping literally billions of stars, and some of those stars are Cepheids. So what Gaia has allowed us to do is to calibrate the Cepheid distances rather better, and then to feed that on to more distant techniques that can be used to get the Hubble constant. So one of the chief proponents of all of this is called Adam Riess, and we'll talk about him in a few minutes. He's another Nobel Prize winner. There's a few of them around in the field of cosmology. And Adam Riess has now got a reported uncertainty of about 1.8% on the Hubble constant, and is arguing for it to be just under 73. So far, so good. But now things get a little intriguing, because while all of that's been unfolding over the last 20 years, another parallel story has been unfolding as well. And that story is about what happened in the very earliest moments after the Big Bang. In fact, elements of the story go back to the 1970s and 80s. So I want to begin by just talking briefly about those. Because it's all very well measuring the expansion rate of the universe today, but one of the reasons we want to do that is so we can answer the question, will the universe expand forever? And that depends on how much matter it contains. So in fact, when Hubble himself was doing this, and then later, colleagues of Hubble, a little younger, people like Alan Sandage, what they were really looking for was evidence if the universe was slowing down enough to make it recollapse. So here's a picture of Hubble at the focal point of the 200-inch reflector in the Palomar Observatory, which for many decades was the largest optical telescope in the world. But measuring this slowing down, well, it proved really hard. To try and do it, it's really back to Star Wars again. You wanted to look at galaxies a long time ago that were far, far away, and you wanted to try to measure the expansion rate of the universe back then and compare that with the expansion rate that we measure today. But try as they might, it was really hard to pin that down because there were so many uncertainties about the properties that galaxies might have billions of years ago compared with today. But actually, one area that was much more successful was to go all the way back to the first few minutes after the Big Bang. There were no galaxies around then, but what we did have at our disposal was the ability to understand the abundances of the lightest chemical elements that ought to exist back then when the universe was very, very hot. So it was possible in work carried out in the 70s and 80s to predict the abundances of deuterium, an isotope of hydrogen with one neutron as well as one proton, and also helium and lithium, and even trace amounts of beryllium as well. And the long story short is that allowed us to develop a theory of what we call nucleosynthesis, the formation of the lightest elements. The heavier elements, those get made in stars, but these lightest elements are primarily, we believe, made during the first few minutes after the universe began. But there was a catch, because the predicted abundance of these isotopes depends on how much matter there is. In fact, a particular type of matter, essentially the atoms that we're made of, that we call baryons. So the baryon density in the first few minutes after the Big Bang affects our predictions for how abundant these different chemical elements ought to be. So this graph looks a little complicated, but what it's really showing is that we can predict how much helium there might be, or how much lithium, or how much deuterium, as a function of the baryon density. So that's running left to right on the horizontal scale. And remarkably, what we find is that there's a range of values for this number, the density of baryons, the number of kilograms per cubic meter, where our theory matches the observations for lithium, for helium, for deuterium. So that's a major success. But the complication is that agreement, the comparison between the observed and the theory, only works. They're in excellent agreement, but only if the baryon density lies in this red zone. So the answer that we've now got to think about is, well, does it? We've got to answer that question. Does the density of baryons match this narrow range that would give us this beautiful agreement between theory and observation for how the lightest chemical elements formed? So we're still working our way back and forth in terms of how this all unfolded. Back in the 70s now, Vera Rubin, she began looking for matter, not in the earliest moments after the Big Bang, like nucleosynthesis had, but in the environs of spiral galaxies. So what she was studying was how rapidly those galaxies were spinning. She could measure that, not by watching them spin, they take way too long for that, but by measuring the Doppler shifts of spectral lines. This time, not due to the expansion of the universe, but genuinely due to the rotation of galaxies, so that one side of the galaxy would be moving away, while the other side would be moving towards. And what Vera Rubin found was that galaxies were spinning faster than they should be if their only gravity was due to the visible stars that we can see. So that led Vera Rubin and other astronomers to a quite remarkable conclusion as well. The conclusion that around a typical galaxy like Andromeda, shown there in the middle, what we think is really there is a spherical halo of dark matter, matter which isn't shining, but is contributing to the gravity to make the galaxies rotate faster. And even more puzzling, the amount of dark matter required to explain how the galaxies rotate seemed to be much more than this theory of nucleosynthesis predicted. Remember the vertical red band? So what that seemed to be arguing was that the dark matter wasn't made of atoms, because if it was, then it would upset that beautiful agreement between theory and observation for the abundance of the lightest chemical elements. And that picture has been reinforced even more in the 30 or so years since Vera Rubin's results, because what we've looked at is the distribution of galaxies in the universe. This isn't the real universe, this is a computer simulation. And what we find is we can match the observed distribution of galaxies in clusters if we put into our simulation a lot of dark matter, but not dark matter that's made of atoms, dark matter that's, well, made of something else. And that's where it starts to get tricky, because we don't know what that dark matter is. We know what it isn't. It can't be made of atoms because of the reasons we've briefly discussed. But pinning down exactly what it is has proved to be very tricky indeed. We've also been able to map the dark matter around clusters of galaxies using a technique called gravitational lensing. So that's the bending of light from background objects due to the presence of matter in the intervening foreground. And that also gives us a story which is consistent with the dark matter not being made of atoms. The way we do that is to compare these lensing maps with information we get from things like X-ray emission from these clusters. And again, they don't match. So whatever the dark matter is, it doesn't seem to be made primarily of atoms. Mapping clusters of galaxies and looking at how those move has revealed even more dark matter. We think there's about 5 times more than the Big Bang nucleosynthesis predicts, and very strongly argues for it not being made of atoms. Now, not too long left, but let's really bring things up to date. And let's begin that by going back to where things stood when I made that first visit to the Highland Astronomy Society in 1998. So around that time, astronomers were still trying to answer this question: is there enough dark matter to ever halt the cosmic expansion? And the efforts they'd undertaken to answer that before had not succeeded. But then there was a new kid on the block, a new way of doing it: exploding stars called supernovae. And what we sought to do with these supernovae was to use them as what are effectively called standard candles. Now, you'll be wondering what that little animation is on the left. So before we talk about standard candles, let's just say a few words about that. What this is showing is the way that a ball, well, okay, thrown unfeasibly high from the surface of a planet, but just to exaggerate it for effect, what you're seeing is that that projectile, let's say it's a ball, is slowing down as it gets further away from the planet. So whatever speed you give it, it will slow down, and that will determine when it stops and when it starts to fall again. So the calculations that cosmologists were seeking to do for the expansion of the universe weren't actually not that different. They were expecting that the universe was slowing down, and they wanted to measure how much it was slowing down to give an indication of how much matter there was, and to try to work out if the universe would ever recollapse again, just like the ball gets up so far and then falls again. So what they did was used supernovae to try and answer this question. And the supernovae, I mentioned already, were standard candles. That meant that we had a very good idea from theory of how bright they really were, and we could compare that with how bright they appeared and get their distance. So this graph, I might even have showed this when I came up in 98, because it was very much hot off the press then. But all you need to take away from this, it does look a bit complicated, is that what Hubble was measuring all those decades before was this straight part in the bottom left corner. But what these distant supernovae in the late 90s were allowing us to do was extend that graph much further, and we got quite a surprise because it seemed to be speeding up instead of slowing down. So what was going on? Well, in 1998, when these results were published, it began to dawn on astronomers that this was an indication that the universe was speeding up in its expansion, and that expansion was possibly driven by something very weird indeed that we've come to now call dark energy. And Adam Riess, that we mentioned before, and his two colleagues, Brian Schmidt and Saul Perlmutter, were later awarded the Nobel Prize for Physics in 2011 for this discovery of the accelerating expansion of the universe. So the very latest results from studying these supernovae at large distances, again, it looks a little complicated, but all you need to note is there's many, many more supernovae we can do this with now, but the story is still consistent. The universe seems to be speeding up and not slowing down. So that's led us to this state of the universe type picture, where only about 5% of the matter and energy in the universe is in the form of atoms, ordinary matter like us. About 27% is in the form of dark matter. We're not sure what that is, but we know what it isn't. It can't be made of atoms, because that would mess up our predictions about the chemical element abundances. And then the dark energy is even stranger. It seems to have this repulsive property of pushing the expansion of the universe apart rather than pulling everything together. So that picture was beginning to emerge in the late 90s. and it's been with us ever since. Despite our best efforts, it really does look as if we live in a universe in which 95% of the matter and energy is in this strange, unknown form. So the final piece of the jigsaw, in my final few minutes, I want to talk about what was happening about 370,000 years after the Big Bang. And this is when the universe had cooled down enough that it had a temperature of about 3,000 degrees, and that was cool enough that the electrons and the protons could combine together. So we talk about this as the era of recombination. It's not really a very good name because the electrons and protons were never combined together before, but the universe had now become cool enough that that could happen. Now, the physics of this is a bit complicated, but all you really need to think about is it's a bit like looking into a fog, because when there's a fog bank, you can't see very far because the molecules are good at scattering light. And that's what the electrons were good at doing before they combined with the protons. So the universe was opaque, just like a fog bank, prior to 370,000 years after the Big Bang, and then the fog cleared. And what we see today is that fog bank. We see a kind of baby photo of the universe, which is light that's coming towards us from that time when things suddenly cleared. There was no longer the scattering of the light that there had been before. We call this the cosmic microwave background radiation, and here's a picture of it. This is from a satellite called Planck that has been revolutionizing our understanding of this. It was first detected in 1965, but what Planck has been able to do is to measure tiny variations in the temperature of that radiation around the sky. So what you're seeing here is a map of the whole sky and variations in temperature at the level of about 100,000th of a degree. Now here's a kind of close-up of it. This is from the first Planck results reported in March 2013, almost exactly 8 years ago. And this was a big deal. I was at a conference in Canada and we just abandoned the session that day. We just poured over the Planck results, and there were a few people from the Planck team at the conference that could explain it all to us. Now, since then, the Planck results have got even better. And what they've allowed us to do is to make this weird looking graph here. This is something called a power spectrum. Details of that don't really matter, but what they tell us about is roughly on what angle scale the variations in temperature are apparent in the map you see below. So what you see is there's a big peak about 1 degree. So, well, that's saying that there's a tendency for the temperature to be related to the neighboring temperature about 1 degree apart. And then all the other features tell us things about what was going on back then as well. So the shape of that curve can be predicted from theory, and it's very sensitive indeed to the ingredients of our cosmological model. How much dark energy, how much atoms, how much dark matter. And what these maps of the cosmic background radiation have allowed us to confirm is that the universe was indeed dominated by dark matter and dark energy. And they've also allowed us to measure, if you like, the shape of space-time, or the geometry of space would be another way to put it. Now, all I want to say about that, but I'll be happy to chat more in the questions if people want to hear more, is that this is to do with telling the difference between a surface that's like a sphere, which we say has a closed geometry, that's like on the right-hand side, or a surface that's flat. Okay, this is actually in 3 dimensions, but we're looking at it in 2 dimensions to simplify things. So it's like a flat piece of paper. Or it can have an open geometry, which is shaped a bit like a Pringle or a saddle. So analysis of the Planck data has allowed us to confirm that we live in a universe where the geometry is like, well, what we call Euclidean geometry, the geometry you learn about at high school. So putting all of that together has given us a fantastically consistent picture of our universe with a flat geometry, a significant amount of dark matter, an even more significant amount of dark energy. But the spanner in the works is that the CMBR also allows us to reverse engineer the current value of the expansion rate of the universe. And that is rather odd, because you think, well, if we know how much dark matter and dark energy there is, we ought to be able to do that. We ought to be able to scale back, well, scale forward might be a better way to put it, from the time when the CMBR was emitted back here, all the way forward to what the Hubble constant ought to be today. But when we try to do that, we get a very surprising answer. So what this graph shows is different ways to measure the Hubble constant. The ones we talked about before involving the Cepheids and Adam Riess, the Nobel Prize winner, those are shown in blue, and they seem to have converged to values of about 72 or 73. But when you try to use data from the cosmic background radiation or other methods that essentially kind of reverse engineer the present day Hubble constant from observations far back in time, then you get a value of about 68. Now, I know the difference between 72 and 68 might not sound like much. And, you know, I grew up when people were arguing if it was 50 or 100. But nonetheless, these little lines that you see drawn, those are what the scientists involved refer to as their error bars, the uncertainty on their measurements. And the annoying and perplexing thing is that both groups are claiming really small error bars, but they don't agree with each other. So where do we stand? Well, this is an even more up-to-date one, and it's got this strange looking number up here, 4.4. That's the Greek letter sigma. That's a kind of way of measuring how significant we think this difference is. Physicists don't usually get too worried if things are discrepant at the level of 1 sigma or 2 sigma. But once you're getting close to 5 sigma, what that is saying is the chances of this just being an accident are really, really small. So there's something weird going on. Either these observations of the early universe are misunderestimating their error bars, to quote George Bush again, or maybe the observations by people like Adam Riess are doing something similar so that actually the values overlap a little better, or we just don't understand all that there is to understand about dark matter and dark energy, or maybe it's both. So that's where things are. And in my final couple of minutes, let me just trail what's going to be coming up in the next few years. Firstly, there's a whole lot of new projects and satellites and telescopes that will be bringing their observations to bear on this big question. And that will range from the James Webb Space Telescope to the extremely large telescope that the Europeans are building in Chile, to the Square Kilometre Array Radio Telescope, to a telescope called WFIRST, which will be looking at specifically this question of the expansion rate of the universe from the perspective of observations like gravitational lensing and some of the other things I've mentioned. And another one that will do a similar type of job is called Euclid. And then there's another one that's really fascinating too, called the Large Synoptic Survey Telescope, or now it's been renamed to the Vera Rubin Observatory in honor of Rubin that we mentioned way back when we were talking about dark matter and rotating galaxies. So that's all coming up in the next decade or so in terms of observations that might shine a light on this question of why we can't seem to measure the expansion rate of the universe correctly. But the other area that's very ripe for fresh development is on the theory side. Our simplest way of explaining the accelerated expansion is in terms of something that we refer to as the cosmological constant associated with the density of energy in the vacuum itself. This relates to ideas that go all the way back to Einstein himself. But maybe Einstein had the last laugh because maybe the cosmological constant isn't actually constant. And maybe there's more going on with dark energy than, well, there's certainly more going on than meets the eye, but there might be more than those simplest theories are saying. So a big focus of all of these observations will be to try and test that, but at the same time, there'll be interesting ideas coming out from theory as well. And you know, some of those theories might be really quite exotic. They might be like some of the stuff that Kip Thorne, one of the Nobel Prize winners for the gravitational wave discovery, was scribbling on the blackboard when he was his science advisor role for the movie Interstellar. So Interstellar is science fiction, but it's probing at ideas about gravity and how gravity really works. Who knows, maybe the truth will indeed prove to be stranger than fiction. And perhaps one part of all that will be searching for gravitational waves. Now, I'm out of time, so I'm not going to do this any justice, but let me just show my final few slides and then I'll be more than happy to talk further if people are interested. I just want to take us back to August 2017, which was a red letter day for LIGO and for our colleagues in Virgo, because we observed not the collision of two black holes, but the collision of two neutron stars. And that was accompanied by a gamma ray burst, and it left behind a very strange object that we call a kilonova. So there's the host galaxy. There's the new kilonova that was observed on that day by optical telescopes, including this one, the SWOPE telescope, that was the first out the traps. And what all of that allowed us to do was to measure the Hubble constant in a completely different way, using gravitational waves to get the distance. Now, from our single measurement, we didn't shed any new ideas or new insight on this discrepancy between values of the Hubble constant. The ones that cluster around 68, well, that's the green band. And the ones that cluster around 73, that's the orange band. And what we got, well, it was in the right ballpark, but with a whopping big uncertainty, because it was only a single binary neutron star. So what we want to do in the coming years, in parallel to all those other experiments that I just showed in the previous slide, is to keep observing gravitational wave sources, measure their distances, measure the redshifts of their host galaxies, and see if we can get our Hubble constant and find out whether it really does settle this debate, this tension over the two different values. Maybe that might even tell us some things about the nature of dark matter and dark energy. So let me just skip a couple of slides. I would say that although we've come a long way in the last 20 years, there's a lot of unanswered questions, a lot of unfinished business. But it seems to me that through a combination of these exciting new observational projects coming up, and also an almost infinite variety of theoretical ideas that will no doubt surface as well, I'm hoping that exploring the dark side of the universe has got a very bright future. Thank you very much.
Thank you, Martin. What is the problem with having varying levels of the Hubble constant, one for early and one for late of the universe? Is there any reason why they couldn't change?
Well, it's just that what one's seeking to do is to extrapolate from the early universe to what the value should be today. And we know how to do that. We know what the mathematical framework is in which to do it. And if what the CMBR is telling us about dark matter and dark energy is correct, then extrapolating a Hubble constant from the CMBR should be straightforward as well. But it just doesn't seem to work. So something's wrong somewhere and we just don't quite know what it is.
Rich asks, which bit of kit do you think will help most to resolve the problem?
Oh, that's a great question. I think it's hard to say precisely, but one of the things that is most important here is to go as deep as you can, because what you want to do is fill in the gap between what we call redshift close to zero, which is where the nearby measurements are made, and then redshift of the CMBR is actually about 1,000. Well, what that means is the universe was only 1,000th of its current size when those CMBR photons were emitted. Wouldn't it be great if we could somehow make measurements that were in between? If we could say what the Hubble constant was based on observations when it was 1/10 of its current size or 1/20th. So probably the instrument that will do best in that respect is the Square Kilometre Array. Because if you go looking for supernovae, there eventually comes a point where they just didn't exist yet. So if you go any further back, you're not going to find any. But with the SKA, we'll be able to see the gas that was around in the very youngest galaxies, even before the stars started to shine. And that will allow us to go a long, long way back, much deeper than some of the other telescopes will.
Thank you. Martin asks, which of the two camps of the Hubble constant do you think is more likely to be right about the observations?
It's very hard to say. I mean, I've worked in both sides of the fence. We're now working, I'm devoting my principal efforts now to the gravitational wave technique, which, okay, our first result was not exactly a spectacular success because it had such a large uncertainty, but we could have got a number that was completely inconsistent with all the other ones. So the fact we're in the right ballpark suggests that everyone is doing more or less the right thing, but we just don't understand precisely where the discrepancies are coming from. I think I lean towards the higher values because, understanding Cepheids doesn't require too much extrapolation. We know Cepheids in our galaxy. We're pretty confident that the ones we see in other nearby galaxies are not that different. So really getting the Hubble constant that way, there's not much can go wrong. Whereas from the CMBR, because it was so long ago, some of these observations have been a fantastic achievement to learn as much as we have about the early universe. But it just leaves you feeling a little worried that you extrapolate all the way from 370,000 years after the Big Bang to nearly 14 billion years. A lot can go wrong in that time. So I think that might be the reason why they're coming in just a bit lower.
And the last question from Rich. When do you think, what would you think will resolve what dark matter energy is? Or is it like fusion energy? It's impossible to work out.
Well, to be honest, we've got a pretty good picture of what dark energy is. I mean, it's not a straightforward one because it seems to relate to phenomena that are very different and far removed from anything we meet in, physics down here on the ground. But the theoretical underpinnings of it all kind of do hang together pretty well. So that's why this discrepancy with the Hubble constant really has thrown a bit of a spanner in the works. So who knows, it could be that in unraveling that one, that we'll realize that we got all the dark energy stuff wrong as well. But I'm not quite prepared to throw that one out yet. I think the fact that the universe seems to be speeding up, that I don't think is a matter for serious dispute now, because that's been tested to death for the last 21 years. The issue isn't, is it speeding up? The issue is, why is it speeding up? And it might well be that we've got to rethink large parts of that.
Thank you very much indeed. Thank you.
Thank you very much for handling the question and answer session tonight. There were some fascinating questions, and Martin, there's quite a few that came through that you didn't get a chance to answer. I was a biochemist, and one of your images actually reminded me of the internal structure of barley. There was large and small starch granules, galaxies embedded in a protein matrix, the dark matter, and contained and connected by the beta-glucan cell walls of the net of the matrix. I always get fascinated by the macro versus the micro scale and how sometimes these images are almost comparable, And anyway,
let me just say that I'll be more than happy to answer the questions offline later, if you can send on the chat to me. As the organisers know, I've been dealing with a misbehaving laptop as well tonight, so I'm relieved that didn't give up the ghost. But again, sorry if I overran by a few minutes, but many, many thanks indeed for the really excellent questions. And as I said, I'll be delighted to answer the others later as best I can, if someone can pass on the chat.
We'll get them to you, Martin. I just want to take this opportunity to thank you very much. Very, very interesting, very thought-provoking as well. You provided a lot of analogies that helps me greatly in understanding some particularly difficult concepts, I have to say. And I'm going to make no apologies for letting you know in advance that I'm going to use them in my presentations and a live webcast from now on.
By all means.
Now, pre-COVID times, Martin, you would be here receiving a token of our appreciation and a thank you card designed and printed by Pauline, but we'll just need to send you them in the old-fashioned way.
Oh, that's
Martin,
really kind.
Thank you very much once again. I hope you can stay with us and experience the rest of our club meeting.
Well, what I'll do is I'll switch to my phone, just in case the laptop battery does finally give up. Yes, indeed, I look forward to that. So thank you again for the invitation.
Cool. And now we go to our club news, astro picks and targets for the month. Pauline's with us again to show you what the club has been getting up to. She's got some stunning photographs taken by us amateur astrophotographers, and she's also going to let us know what to look for in the spring night sky. Pauline, over to you.
Thank you very much, Eric. Right, hello everyone. We are going to have a look at Auriga tonight, who is the charioteer. And Auriga is identified with a number of prominent people in Greek legend who are associated in some way with a chariot, which at the time was very important in Greek society. But the constellation is also associated with a herd of goats. Capella represents the female goat. So this is Capella the star, brightest star in the constellation. And she represents the female goat Almathea, which suckled baby Zeus. And then the stars Eta and Zeta, well, let me get my pointer on. Sorry. So here are Eta and Zeta, her kids. And Auriga is often shown holding the reins of a chariot with his right hand, but also carrying a goat on his left shoulder and cradling her kids in his arm. Now, some depictions of the constellation show Auriga's hat, which you can see here. And then some depictions will also show a different way of joining the dots on the right-hand side. Generally, though, without the hat star, which we really don't need, and it's actually quite tricky to see the hat star. The rest of the stars in the constellation are nice and bright and very easy to find. And I want you to have a look at this triangle here. This is an asterism, which I will mention in a little while. So if we join the dots, that's what we get. And if you look above Orion, you will find Auriga quite nicely. And if you remember, Capella is part of the winter circle. So it's an easy constellation to find, but always find Orion first, and then you can find Auriga. Now, there are a couple of interesting things about Auriga. It's at the galactic anticenter, which means it's at the point in the sky opposite to the center of the Milky Way as viewed from the Earth. So Sagittarius is usually considered to be the center of the galaxy. So 180 degrees away, either here or here. But here you can actually see Capella. This is Auriga, and this is the star that it shares with Taurus. So this is the galactic anticenter, which just happens to be Auriga. And then the other thing to say is that if you look at Vega and Capella and join a line between them, they almost pass through Polaris, and they are almost equidistant from each other. So that's just two little extra bits there. Now, Capella itself, as I've said, it's the brightest star. It means she-goat. That's why it's associated with Almathea, the goat that suckled Zeus. And it's the sixth brightest star in the whole sky. It's a yellow star, magnitude 0.1. And it's a quadruple star system. So it consists of two yellow giant stars, and these orbit each other every 104 days, but so closely that you cannot actually separate them. And you only know they are a binary system because of their spectra. So this is a spectroscopic binary star. And then the other component of this system, or components, is a binary pair of two small red dwarf stars. Now, these can be separated, but you need a very big telescope in order to see them. And then just below Capella is that asterism that I showed you, the one with the three stars in a triangle. So we have Epsilon and Eta and Zeta. And Eta and Zeta, which are the kids, are also called Hadai, which means kids. And there they are in the constellation of Auriga, very easy to find. Now, Epsilon is actually a very interesting star. It's an eclipsing binary with a white supergiant and a dark companion. And this dark companion is thought to be a dark disk like this. And every 27 years, it goes in front of the white supergiant. And normally at magnitude 3, it drops to magnitude 4 and then can last, this dimming can last for up to 2 years. And then Eta and Zeta are a really nice contrasting pair of colors. So blue, white, and this is an orange giant. It's actually an eclipsing binary with a smaller blue star, but you'll only see the orange giant. The colors are better seen in a small telescope rather than binoculars. Beta, the star Beta down here, is actually Beta Tauri. This is the star that Auriga shares with Taurus. So this forms one of Taurus's horns. But the star itself has actually been assigned to the Taurus constellation. And it's called Elnath or Alnath. Now, if you're looking round the sky, one of the stars which is worth checking out is this one. It's a W Aurigae or UU. It is a variable star, changes from magnitude 5 to 7. You won't see this easily with the naked eye. You certainly won't see it when it goes down to 7, but you can find it with binoculars. Except that you're probably thinking, but there's so many stars out there. Well, fortunately, it has a very deep red color here. And that makes it a lot easier to see. Although I have searched for it, I haven't actually found it yet. So it's something that you can look for. And while you're in the vicinity, you can find this small open star cluster. It's supposed to look like a crescent, bit of imagination required, I think. And then there are 4 bright stars around the outside, which look a little bit like a stretched diamond. And then the other open star cluster worth looking for is this one, known as the kite cluster, because guess what? It's in a kite shape. Now, although you can see it with binoculars, you'll have a bit of difficulty making out the kite shape. So you're better with a low power, small telescope. The best star clusters in Auriga are M36, 37, and 38, and these can be easily found with binoculars. In fact, M36 and M37 can be seen naked eye from a dark sky site, usually best to use averted vision where you're just looking very slightly to the side of the cluster itself. So if we have a look at M36, it's a beautiful little cluster, about 60 stars or so, nice magnitude, so it's an easy binocular object. M37, which is outside the lines making up Auriga, is the best star cluster of all. It has this almost triangular shape here. It's got about 150 stars. You can see it very easily with binoculars, but through a telescope, the stars resolve into stardust, which is what they say, and it's very true. It is really beautiful through a telescope. M38 is really not that brilliant to look at, certainly not under a magnification. There are about 100 scattered stars, and it's better to use maybe a small telescope with a wide angle lens, and you get a better view here. But you can also see a smaller star cluster over here, and this is NGC 1907. And then we have this object. IC405 is simply the catalogue name, but it's also known as the Flaming Star Nebula. And it's really rather beautiful. It's a reflection emission nebula lit up by this star here called AE Aurigae. And this is the reflection part. This is the blue where there's lots of dust, and the dust reflects the light from this star. And then the red is supposed to be the hydrogen, which is the emission part of the nebula, which gets excited from the radiation from this star. And AE Aurigae is an interesting star. It's thought to be a runaway star, perhaps ejected from the trapezium cluster when 2 groups collided. And the trapezium cluster is, of course, in the Great Orion Nebula. Now, I hadn't realized that this area of Auriga had so much nebulosity. It's really rather beautiful. This is the Flaming Star Nebula. This is IC 410. And we've got the 2 star clusters M38 and M36. This is a supernova remnant. And this star is the one that is shared with between Taurus and Auriga. So if you turn this picture up so it's almost vertical, very slightly over to the left, then this is where you find it. So there is the star that's shared with Auriga and Taurus, and here is the 2 star clusters. So if we now look at the sky, the things that are in the sky, just to let you know that spring equinox occurs on the 20th of March. So, you know, it's not long before we get into warmer days. The clocks spring forward on the 28th of March. We lose our dark evenings. New moon 13th of March and the full moon on the 28th of March. There aren't very many visible planets around at the moment. So even though we've got a nice grouping of Mercury, Jupiter and Saturn plus the crescent moon, you are unlikely to see them. You might see Jupiter because it's really quite bright. And that's because the ecliptic in the morning, because this is, sorry, I should have said this is morning before sunrise, and the ecliptic is tilted at a very steep angle. And the ecliptic is the apparent path of the sun and the planets. And because it's tilted so much, it means that these planets never quite leave the glow of sunrise. And Venus is hidden by the sun at the moment, but it will become an evening star in a month or so. Now we do still see Mars. Lovely photo opportunity with Mars passing by the Pleiades, and I saw it last night. I tried taking a few photographs, which are rubbish, unfortunately, but it's well worth looking out for, although I think the weather is going to be changing over the next week. And then we have the waxing crescent moon passing through Taurus. We know it's Taurus because we've got the Pleiades and Aldebaran, the eye of the bull. So on the 18th, the moon is close to the Pleiades. So that's another photo opportunity. 19th, we've got the crescent moon with Mars and Aldebaran. And I was quite astonished to realize that Mars has faded so much over the last couple of months ago that Aldebaran is now brighter than Mars. And there's something else to look out for, is the zodiacal light. Now this is something I have never seen, and it's visible from late February through March to early April. It looks like a faint, hazy pyramid of light in the west after sunset. Here are the Pleiades to give you an indication of where to look. And in the autumn, you can see the zodiacal light before sunrise. So the two quite different. So after sunset in the spring, before sunrise in the morning. And I'll explain why in a moment. But you must be in a dark sky site, no moon visible, no light pollution. Although sometimes apparently people will look at this and think, oh, there must be a city because it looks like the sky glow from light pollution. You can see it after it's got properly dark, and it can be seen for up to an hour. The reason we see the zodiacal light at this time of year is because the ecliptic stands nearly straight up with respect to the horizon. And you remember that I said in the morning at this time of year, the ecliptic is at a very steep angle, so you're not likely to see the planets down here. But in the evening, the ecliptic is quite different, and this is when it stands straight up, or virtually straight up. And this reverses in the autumn. So we have a tilted ecliptic in the autumn and a nice straight up and down, virtually straight up and down one in the morning in the autumn. And the a zodiacal light itself appears to extend from the sun, where it's set in the west, all the way through the zodiacal constellations, because this is where you find the ecliptic. And when we see the zodiacal light, we're actually looking sideways into the plane of our solar system. Don't forget, all the planets orbit in the same plane as the Earth as they move around the sun. So this is your dust cloud. And the zodiacal light is actually sunlight reflecting off the dust particles that move in the same plane as Earth and the other planets orbiting our sun. So this is the zodiacal light here. So in theory, you could see it extending from the west to the east. That'll be a planet. But also notice it is not coincident with the Milky Way. Here's the zodiacal light. Here, this is from the European Southern Observatory. That'll be a planet. And there you have the Milky Way. Good news, we have 3 spacecraft newly arrived at Mars. So we have the Hope orbiter from the United Arab Emirates. And basically, it's going to try and understand how Mars has gone from warm and wet to cold and dry. So it's doing something similar to MAVEN, but not quite. We also have Taiwan 1 from China orbiting Mars, and it's going to study the high atmosphere and the structures and composition of the surface. And a rover will hopefully land in May or June. And then, of course, we have Perseverance. And I don't know who, well, I know a few people watched the live landing, which was just nail-biting, but it was fantastic when they said, yes, it's landed safely from the telemetry they were receiving. And then, of course, they got the video after that. And this is all because of the time delay. But then they received the video, which you can actually watch as the sky crane, which you're looking at the underneath of. Here are the tethers, and the tethers are attached to the rover, so you can see it actually, the rover actually being lowered to the ground. And this is an artist's impression of what it would look like. And I'll put a link into the Stargazy Pi so that you've got that, but it's out there on the internet, so I'm sure you'll find it. Now, one thing I didn't know was that the parachute has a code within it. And this spells out the coordinates of NASA's Jet Propulsion Laboratory, as well as its motto, to dare mighty things. And Perseverance hopes to sample the sediments really close or at the delta if possible, which is thought to be around 2 kilometers to the northwest, because it's going to be looking for past microbial life. It will also take core samples and stash them. And this is for a return mission to collect. So Perseverance is actually really important because it is the first of 3 missions. So Perseverance will take the samples, stash them to the side. Another mission will come down, land, pick them up, go back into orbit, stay there until a 3rd mission comes along, and then that will take all the samples back to Earth. So Perseverance really did have to work. Now, with Club News, Eric has already mentioned that we have the AGM in April and that the office bearers will stay the same. But don't forget, if you wish to stand or nominate anyone, let Rona know. And if there are any items for the agenda, please let Rona know. One other thing that we would like to ask you, is there anyone with website experience that could help to redo our website? I was hoping Eric was going to say a little bit more about this. The website now is not considered as safe as it could be, if that's the right term. It's still perfectly fine, but somebody could get in and mess around with it. So we really need to change the website. So help, please, there. Live observing sessions, I think, as Eric mentioned, they will occur depending on the weather and the phase of the moon. Notification by WhatsApp and Facebook, because they're more instant. Now, I've joined the WhatsApp group. It's very easy. And in fact, it alerted us to an aurora last night, although the aurora was quite dim, really. And then, as Eric also said, think about what you want for our club, which direction you would like our club to go in. We're going to get some ideas together. We would love your views and opinions, please. Finally, Caithness Astronomy Group have teamed up with Caithness International Science Festival to run a number of events during the month of March. And the first one is the 6th of March, and that's this Saturday. Information is available at these websites, and I'll also put all this information into Stargazy Pi. So now for the best bit. Here we have a beautiful picture of Sirius, which is of course our brightest star. And this is Sirius that Eric has taken. He's defocused the star and taken lots of pictures in quick succession. And it just shows you how the star changes in color. So now he's taken or separated the photographs a little bit so that you can see more of the star itself. And finally, with these, you've got definite colors, certainly, especially in the beginning part. And this happens because Sirius is low down in the sky. It's in a thick part of our atmosphere. And because of that, it just wobbles and changes in color and movement. And Sirius, as well as Venus, are the two objects that are most often mistaken for UFOs in the sky. But the way this has been presented and achieved is absolutely beautiful. I love it, Eric. We have a few more stars, excuse me. And these are the Pleiades. And here we have Eric using his all-sky camera, where he points out this is a bright flaring satellite, not a boloid, but this one is actually a meteor, a fireball or a boloid. And he has reported this to the UK Meteor section. We have a number of beautiful moon pictures by Dave. So we start with the crescent. Then we have a waxing crescent. And this is just over half full on its way to gibbous. And I want you to look at this area up here. This is the Imbrium Basin. So if you have a look at this area here, you see this is the crater of Plato. This is the Imbrium Basin. And this is like a little ear that comes off the side of it, little mouse's ear. And this is known as the Sinus Irium. And if we turn that picture upside down, you know, those two little craters there, and Dave has labeled this the Promontorium Heraclides. Oh, I had that right before this, before this moment. And further down the moon, we have Copernicus with the double peak, Borealdus crater, Tycho, and Clavius. Now, this is an interesting crater, which we will see in close-up a little bit later on. I love the daytime photographs, always very atmospheric. And this is 3 days before full moon. So if we go back to the evening again, we have 3 nice craters within the Imbrium Basin. And I'll leave you to pronounce those. And this is Clavius crater. And the reason it's unusual is because it's got a series of craters or little craterlets getting smaller and smaller in this lovely curve. Difficult photograph to take in close up because it's right at the bottom of the moon. So you've done well, Dave. And then we have moonrise a day before full moon, which is beautiful. And we have Anthony joining us for a photograph for the first time. This was moonrise at full moon. And again, full moon with beautifully framed by these trees. And this is a very unusual picture, Dave. And I'd meant to ask you about it. So this is the sun with prominences, but it's on a starry background, and we've got this really ethereal flare here. So very, very atmospheric, very unusual picture. And now we have a number of deep sky objects, all of which are just incredible. So Mark from Stornoway is showing us the Fireworks Galaxy, and this is found on the border between Cepheus and Cygnus. And to the side is NGC 6939, it's an open star cluster. Andy Yearley is another newcomer to our photography part. This is the Pinwheel Galaxy in M101, and it's found in Ursa Major. Look at this lovely bright center. This is the Elephant's Trunk Nebula by Mark. It does extend a little bit further, but it's quite incredible. It's thought to be a star-forming region, and it's found in Cepheus. And here we have the Bubble Nebula in Cassiopeia. And the whole area is just incredible. This is a really good picture. And the Bubble Nebula is actually blown by a Wolf-Rayet star, which is an enormous star that's extremely hot with very powerful winds. And how about the Jellyfish Nebula? You can really see the gelatinous portion of this nebula is absolutely incredible. So you've captured this really well. It's a supernova remnant, and it's found in Gemini. This is one of my favorites. This is the Iris Nebula. It's a reflection nebula. You can see the blue within it. So it'll be full of dust particles which are reflecting the light from this central star. And this is found in Cepheus. This is my other favorite. This is my, I've got three favorites. One will be at the very end, but this is my other favorite, Rossetti Nebula by Eric. And there is a story behind this, which he has given me permission to share. You'll notice the date is the 14th of February. Eric forgot Valentine's Day, and Marion was not best pleased. So what did he do? He went outside to do some astrophotography. But fortunately, it was of a rose to make up for the red roses that he should have brought her for Valentine's Day, but didn't. So I hope you're going to get this framed, and then you can present that to Marion instead. And a couple of days later, we have Eric again with the two galaxies close together, M81 and M82. This is the Cigar Galaxy. Beautiful. And of course, M42, the Great Orion Nebula, always a lovely photographic object by Dave. And now we're going to come on to the Aurora photographs, which I absolutely love. So Sue has certainly been very busy, taking lots of pictures. I'm not going to say very much. And this is the 4th. And then on the 16th, we have a few more. Look at this beautiful deep green. On the 20th, you'll see lots of rays, absolutely gorgeous. And Alan Butterfield from Elgin has taken a picture of the aurora from Lossiemouth Beach. And again, look at all these rays that you've got and the different colors, especially in this photograph here. This is absolutely gorgeous. And the last aurora photograph is by Ian Hall, taken on the 24th. Beautifully ethereal picture, this one. And this is my most favorite picture, which is why I've left it until last. This is another newcomer, Freck Fraser from Belladrum, and full moon, the snow moon rising. It's absolutely beautiful. And I'm going to finish with, this is all I could manage this month, just to say thank you very much. And also to look out for the sun as it moves along the horizon. This is my northwestern horizon. And I now can watch the sun as it moves really quickly to the point of equinox, because this is the time of year when the sun seems to move very quickly along the horizon, both in the morning and in the evening. And I think this is my equinox, but I'm not entirely sure. So that's it. Thank you very much, everyone.
Thank you very much for that, Pauline. Simply superb. You've given us great targets to aim for, and we'll probably include some of those in our live observing webcasts, I think. The one new one you've given me is that M36, M38 region. I also didn't realise it had so much nebulosity in it. And
Yeah.
I think with my narrowband filters, I might have a go at it. And I can see Mark was on there. He'd probably have a go at that as well.
I think you probably could.
that
Yeah.
looks pretty good.
They're beautiful.
All amazing amateur astrophotographs. Can I just thank all the contributors in our astronomy clubs and all the groups across the north of Scotland. Well, that is just about us for tonight. If you want to join us for a wee blether, please click on the link, which I am hoping will be showing in the chat box. In fact, I can see it now. Rich has just put it in there. You'll see a screen or a box once you've clicked it telling you that the meeting is yet to start, and it will just take a minute or two for Rich to open the chat room. So if you just hang on till it does, it will definitely open, and then we can just talk about anything and everything we want. So to all of you, thanks once again for coming along. Until next time, clear skies and keep looking up.